force that you feel will change. The change of momentum doesn't change. The impulse doesn't change. The variables change. The force and time. More force, less time. More time, less force. That's it. But they both have the same impulse because the change of momentum is the same. It's another question that you have to be careful with. Let's leave this. Okay, there's one example. In a particular crash, you have a mass, you have a car moving. Find that's a very easy problem. So, how good are bumpers, airbag? Yeah, bumpers on the car, right? So they give you a car moving to the west, and then it crashes, but it bounces back with some speed. What is the impulse? Okay. So that's very simple. You put here before the collision. We're going to be using this in collisions in a bit. Before the collision, you have the wall and the car 1,500 kilograms is moving at minus 15 I meters per second. After this car is going with 2.60 I. So, application of formula basically or equation. Right? Final vector, the initial vector, the final will be that. Minus so clearly minus and minus will add. I can factorize 1,500. And I will get I. All right, the magnitude will just be this. That's your impulse. And they tell you that if the collision lasts for 0.15 seconds, let's find the force. Now the collision. Force times time, or force times 0.15 equals to that. Don't forget the I. That gives you the direction of the force. To the right is 1.76 times 10 to the 5 I All right. So let's start talking about collisions, guys. We're going to be studying on this course collisions on one dimension and then two dimensions. There are three different types of collisions that you should know. And we're going to be focusing the most on two of those. The three different types of collisions are elastic, complete or perfect inelastic, and inelastic collision. What's funny is that in everyday life, inelastic may be the most common type of collision. In every collision, momentum is conserved. We know that by the definition of an isolated and a non-isolated system. But elastic collisions, which is the one that we're going to do right now, has the particular property that the kinetic energy before is equal to the kinetic energy after the collision. So the energy is conserved. The energy of the system, if you have two masses, the energy of one before plus the energy of two before is equal to the energy of one after plus the, we will do the equations and you will see how it all works out. However, that doesn't seem very realistic. When you have a collision, guys, there is always some loss of energy. There's always some energy being released. As we discussed in the energy chapter with the work energy theorem on friction. Friction, for example, is a way for energy not to be conserved. Sound, mechanical waves, heat, right? So the reason why we study elastic collisions is because there are environments where it may actually be almost true. For example, in when we study particle physics, for example, in the Compton effect that you guys will study probably if you get into physics, higher order physics, right? We're talking about subatomic particles, right? Where gravity doesn't really play a role, where there's no friction between particles. So in that case, and that's the whole concept of ideal gases, right? An ideal gas on chemistry is a gas where the particles are bouncing with each other and no energy is being lost. And also with the walls of the container. So what about the other collision, perfect or complete inelastic? That is when you have a mass crashing or colliding with another mass and they stick together. That's actually the easiest type of collision. And we're going to do a few problems on that. So let's analyze that one actually. Let's analyze perfect inelastic and elastic collisions. So if you have a mass M1 going with some velocity V1 and is about to have a head-on collision with a mass M2 with this velocity, and then after the collision they stick together, So after the collision, they stick, they travel. So the conservation of momentum says that the momentum before the collision has to be equal to the momentum after the collision. What's the momentum before the collision? M1, V1, plus M2, V2 vector equals to, they stick together, M1 plus M2. So my objective most of the time is to find this V. V becomes M1, 1 plus M2, V2 over M1. Obviously, if V2 in terms of magnitude is greater than V1, but V2 is going to the left, so V2 will be more negative. So you may get a negative value of V. What's the meaning of a negative value of V? It's just that it's traveling. So that's simple to start. This is a more interesting one. This is the elastic collision. And we're going to be doing problems on that. So an elastic collision is the same situation, but after the collision, they don't stick. They just move, and let's illustrate it. So let's erase this for now. I mean, this is also in the slides, but so you can see it. Now, after the collision, so V1 initial, V2 initial, V1 final, V2 final. And it's elastic, right? By conservation of momentum, M1, V1 initial, plus M2, V2 initial, equals to M1, V1 final, plus M2, V. So if I give you the initial velocities and you know the masses, you still have two variables. So how do you work out a problem like that? So there is another condition, right? For an elastic collision, the kinetic energy initial is equal to the kinetic energy final. One half M1 V1 initial square plus one half M2 V2 initial square is equal to one half M1 V1 final square plus one half M2. And you may be thinking that's going to be a mess. Not really. First of all, one half, 1 half, 1 half. I mean, it's like multiplying. Let's join M1s with M1s. M1 parenthesis B1 initial square minus B1 final square. I can do that. That's fair. And I can do this. M2 B2 final square minus B2 initial square. Now, let's take a look at this equation. I can also do what I did there. M1s with M1s. So from here, M1, B1 initial, B1 final equals to M2, B2 final, right? B2 initial. I already see what I want to do, right? What I can do is, there's something you need to remember from algebra. A squared minus B squared, A squared minus B squared, right? It's like a difference of squares. So this equation here, I can write like this. And what I can do now is I can divide the equations. I can do this. If I divide that, M1 cancels, B1 minus B1, B1. So I get 1 over B1 initial plus B1 final. And here, 2 will cancel. This with that. 1 over B2 final. So look at the simplification. If I do cross product, I get this. B1 initial plus B1 final equals to B2 initial to final. Now, you never find equation like that. What you're going to find on a textbook, any other textbook, is this equation. So I rearrange that in terms of relative velocities before and after the collision. So B1 initial minus B2 initial is equal to minus parenthesis B1 final minus B2. That's only true on elastic collisions. Why do they write the equation like that? Because this is B1 with respect to B2 initial. B1 with respect to B2 final. And the minus is because this goes as negative, right? This goes to this side, so I have to put a negative side. This proof, I think I actually left it on the slide because, yeah, I left it on the slide so you can see it there. But there are more situations, of course. Or there are, like, you will understand this when we do the problems. So that's the summary of elastic collisions. And we did already perfect in elastic. Now, are we going to study in elastic? Not really. I mean, the only way you can study in elastic collisions is if you are given, because this is not true in elastic collisions. Energy is not conserved, right? You go into a more realistic scenario. So how can you analyze an inelastic collisions? You need to be given information related to the energy before and after the collision. And that's given by something called the E coefficient or collision coefficient, which is normally less than 1. And it tells you what's the percentage of the energy being conserved. So normally what you have is that this divided by this is equal to that fraction. Don't worry about it. We're not going to do that. We could, but at the end of the day, the learning goal is to understand momentum and how to use it in problems. So with this, I'm perfect inelastic is more than. All right, so let's take a look at some of those slides, and then we can start doing some problems on both collisions and some situations with momentum. So in a perfectly inelastic one-dimensional collision between two objects, what condition alone is necessary so the final kinetic energy of the system? Okay, so remember guys, for perfect inelastic collision, energy is also not conserved. Okay, just remember that. It makes sense, right? You are sticking the masses together, so it cannot be conserved. What condition alone is necessary so that kinetic energy? But there is a condition for the masses that are coming towards each other, or they might not be coming towards each other. They don't tell you that, right? But there's a condition for the system to have no energy after the collision. Guys, if the masses are sticking together after the collision and you want them to have no kinetic energy, what should be the speed of the system after the collision? If you want the system to be with zero energy, guys, the system should have zero speed. If you want the system to have zero speed, the momentum of the objects individually before the collision should add up to 0. So let's take a look at the options. The same mass, no. The same initial velocity, no. The objects must have the objects must have initial momentum with the same magnitude. There you go. So if they both have the same magnitude of momentum in opposite directions, the momentum will cancel and will make it for zero momentum after the collision, zero speed, zero kinetic energy. So these conceptual questions are very interesting. They actually reinforce some of the concepts, so I think it's important that you understand them, okay? A table tennis ball is thrown, so a table tennis, you know, is a very, it's not tiny, but it's very low massive, very light ball, right? It makes a one-dimensional elastic collision and bounces back along the same line. Compared with a bowling ball after the collision, the table tennis has a larger magnitude of momentum and more kinetic energy. Be careful with that because remember that the masses are different, right? Okay. The momentum of the tennis ball initial plus the momentum of the bowling ball initial is equal to the momentum of the tennis ball final plus the momentum of the bowling ball final. Right? Now, the bowling ball has zero momentum because it's stationary. So the table tennis gives some of the initial momentum to the bowling ball to move. So momentum of the tennis ball initial is equal to momentum of the tennis ball final plus momentum of the bowling ball final. So it cannot have a larger momentum. It needs to be smaller. It cannot be the same either. Right? Compared with the bowling ball after the collision, the table tennis has, because compared with the bowling ball after the collision, the table tennis has tennis ball initial minus momentum ball final equals to momentum. It has a smaller momentum. You know why? Because if you put it in the equation, the momentum after the collision is negative. So when you do the equation, you will have that the momentums before and after of the tennis ball add up to the momentum of the bowling ball. Now, in terms of kinetic energy, it should have less kinetic energy as well, right? Oh, more kinetic energy. Let me see. So it has a small amount of more kinetic energy. MV1, MVB, MT. What the momentum, so velocity. Velocity is. Oh, yeah, I forgot about the mass of the. Yeah, so because the mass of the bowling ball is much larger, it will have way less speed. So, yeah, that's my bad. The smaller momentum makes sense because all the momentum has been transferred, not all, but a large part of the momentum has been transferred to the bowling ball to make it move, but it will move regardless of how fast, right? Because of the because of the large difference between masses, the bowling ball will move with a much smaller speed, which will make it for a smaller energy, right? So the table tennis will have a larger kinetic energy. Okay, so these are some strategies that you have here for the collisions, all right? You have there for perfect inelastic and elastic collisions. And let's take a look at from the book, okay? And then we have the ballistic pendulum, yes. Okay. So we're gonna do two problems of perfect inelastic collisions. And at least one problem of elastic collisions. So now I'm gonna do examples, okay? From the book, when they give you this, you have two ends of two tables. One and table two. And what they give you is they give you a wooden block. Like that. And the mass of the block is 1.25 kilograms. A 5-gram bullet, not a bullet here, is fired through the gap, and it's going to stick inside a wooden block. Now, this is a 5-gram bullet, and the magnitude, right, the speed, you don't know. You don't know. Now, after the collision, the block and the bullet rise 22 centimeters. So after the collision, the bullet block system, they go up. Let's put here the bullet. The tables were here. Right? And this is it went up. Makes sense, right? Find the velocity, find the speed of the bullet before the collision. So this is a problem where you have to use different concepts. Let's remember that because the block is going up, it's going against gravity. The block was just resting there, right? And then why does the block go up? The block goes up because it gains energy to go up. The only forces acting between this point and this point, the only force is the force of gravity, which is a conservative force. Therefore, the block goes up due to energy transfer. And what's that energy transfer? A and B. Energy on A is equal to energy on B. What's the energy on A? Is when the bullet hits the block. So this will be kinetic energy. Mass of the bullet plus mass of the wooden block times velocity prime square. Because this gets some B prime. Not V. The bullet doesn't, the bullet due to the friction or after the collision loses some energy. B prime. Energy at B is just gravitational potential energy or potential energy due to gravity. M, G, and what's H? Point. So, and I can find B prime. B prime will be 0.22 times gravity is 2, square root of that. $2.1 and what's B prime? B prime is the velocity of the system when they stick together after the collision. So if we analyze the collision now, so let's put here for the perfect inelastic collision. The momentum before, so the momentum of the bullet is equal to the momentum of the bullet plus wooden block. Pretty much that's why it is, right? You can just wait like that. Mass of the bullet in kilograms times the speed of the bullet is equal to mass of the bullet plus mass of the wooden block that times the velocity after the collision, which is 2. If I do that, I get 527 meters per second. Again, it's a perfect example of how previous topics, they get related, right? They come back. Let's do a ballistic pendulum. In the assignment, there is a problem about, well, the problem I'm gonna do is a pendulum that is hanging, and then again a bullet makes it slanted, right? Makes it oscillate, but it doesn't make it go into a full circle. In the assignment, there is a problem later. There is a video I have in Canvas where I go over that problem. But pretty much, if you are dealing with a circle, right, you have to think in terms of centripetal force, etc. But in this one here, it's the same. We're going to be combining momentum with conservation of energy. So that was one example there. Let's take a look here. Okay, they don't give you values, so let's just use variables. Okay. Ballistic pendulum is an experiment that you can do in a lab. You can perform this experiment in the lab. I don't know if you're going to do that this semester, but it's very interesting to see where the energy goes, how the collision happens, and how momentum is conserved. So what is ballistic pendulum? You are given that M, and then a bullet with mass little m, again, with some velocity, is going to strike the mass, stick on it, and it's going to rise. What? Let's make it bigger so you can see. So that's that. And after the collision, this will lift. Like that. M plus little m. And with respect to this point is a height h, gravity that, and then you're given an angle. They don't tell you what's h. They give you this m. So clearly the figure is not to scale, but it's the same pendulum. So I know that it is also M. What can I say about H? This is L sine theta. So this is L sine. So from the figure, H is equal to L minus L cosine theta. That's the first step. Okay. The mass, just like the problem that we did, is going to be lifted some height h due to some energy that the mass is acquiring. Where is that energy getting or coming from? Bullet. But we know that there is going to be a perfect inelastic collision. So I can say that the mass is going to be lifted with a v prime speed or velocity towards the right. So if I put here the collision first, the momentum of the bullet is equal to the momentum of the mass plus bullet system. The momentum of the bullet is little m v. This will be m plus little m times v prime. That's your first equation. Conservation of momentum. Right? And v plus 0 equals to m plus m times v. It's basically what we did in the proof, right? Or the illustration. Now the energy, conservation of energy. We have 1/2 m plus little m v prime squared, that's the energy it uses to take off, equals to m plus m times gravity times height. But hey, how is this? Right? So what's v prime? Do I look for v prime? No, I'm looking for v. So now I put this. If I do my algebra, v of the bullet before the collision is m plus m divided by little m Don't memorize the formula. It can be a bit right. But just look how it's solved. That's basically your ballistic pendulum there. So 2 examples of perfect inelastic collisions there. Let's do now the elastic collision example. And after that, we have to go into 2-dimensional. Yeah, that's actually easy. Answer más. Perfect. All right. So now, for the elastic collisions, you're gonna have 2 masses. They're gonna collide. Well, I'm gonna use the example from the book. All right. One of the masses has a spring, so we can extend on the given question. All right. But the technique is the same. You're given M1 and M2. Let's put here sample M1. Which is 1.6, so 1.60 kilograms. Moving at 4i 4.00i meters per second is on a head-on collision. It's about to have a head-on collision, but This guy has a spring. The mass M2 is of 2.10 and is heading with a velocity of negative 2.50 I. Find the velocities of the blocks when they are after the collision. So they're going to come together, the spring is going to compress, and then they're going to. So V1 final and V2 final. Look, obviously, the blocks are going to be going like that. Doesn't matter. Let's take a look at the conservation of momentum. So, momentum before is equal to momentum after. 1.60 M1 times V1 you can put the I, but it doesn't really matter because the final is also going to be the I direction. The signs is what we have to be careful of. Minus 2.5. And minus comes from them, right? Before is equal 1.60 V1 final plus 2.10 V2. But we have two variables. Hey, it's elastic collision, right? For an elastic collision, there is an important condition. V1 initial minus V2 initial equals to minus V1 final minus V2 final. This has to be written down. Formula sheet. Okay? So if I use this condition, V1 initial 4. V2 initial right? There. Equals to well, I can put here minus V1 final plus V2 final. Perfect. Two set of equations with two variables. Let's simplify these two equations. So this equation here becomes what? This becomes 6.40. Oh. So we have to take a look at that first. $5.25. So this is 1.15 equals to 1.60 V2 or V1 final plus 2.10 V2 final. That's this. This one will be 6.50 equals to V2 final minus V1 final. So what can I do in these two equations? V1 final, 1.6, 2.1, positive V2 final, V2 final. Hey, I have negative one. Let's multiply the second equation by 1.6. If I do that, right? If I do that, I get this. The first equation is the same. Second equation from this. 10.4 equals to if I add the equations now, this cancel with that. This becomes 11.55 equals to 3.70. V2 final, as we were expecting, will be positive. $3.12. All right. But that's not enough. I need to get V1 final. Let's start with this equation. Remember this equation? 6.50 equals to V2 final minus V1 final. Guess what? You're gonna get V1 final to be negative because V2 final is that. This went minus that. V1 final will be negative 3.38 meters per second. Is that it? Puedes ayudar, correcto. Yeah. There you are. This is the very good example, guys, of elastic collisions. Now, that will be a long problem. Be careful with the signs, with this condition, and the rest is algebra. Now, this will be the hard situation. There is a more simple situation that when I have done this in school, we do the following situation, which is part B. Normally, what we do is we give one of the final speeds, velocities. Right? So you basically give 3 velocities, not just 2. So you don't have to do the second condition. The conditioner. So part 1 is that. Part 2 will be find V2 final at the moment where V1 final is 3 meters per second. So before they come apart. Let's do that. Okay? So those speeds are when the masses are after they collide, they go to the right and to the left respectively. Part B. Okay. I will leave that in there. Part B We don't need this now. We don't need this. That's always true. But part B, find B2 final when at the moment when B1 final is equal to 3.00 positive. So that's, if you want to draw the picture of that, it will be at the moment where the masses are sort of stick together. They are not really stick together, right? But mass 1 is here, is in contact with the spring and is stretched a little bit, and M2 is here. So here is free. So you want to find very easy, guys. But you know why? Because you're basically given this. So this is 6.40 minus, let's do this multiplication again. I replace that with free, and I'm just looking for B2 final. See what we get. That's 4.8. Perfect. I get the B2 final. If you guys do the math, minus 1.74. Because makes sense, B2 is going to. All right, so that's the easy situation. If I give you free velocities. Now, what about that spring? Part C, they give you the constant on the spring, 600 newtons per meter. They want to know at this instant, what's the value of X, the compression. So guys, even though this is an elastic collision, at the moment where the spring is being compressed, that spring is absorbing energy of the collision. Only when the spring is totally unstretched, that's when the energy it goes back to kinetic, right? That's why I was able to find with the condition this. At this point, part of the energy of 1 and 2 is going to the spring. The leftover energy. What do I mean by that? This block has some energy. 1 has mass v squared. Minus whatever energy is being released here. Plus this energy minus the energy here, which I know now because I have the speed. Magnitude speed. That difference of energies is equal to the energy of the spring. Let's write it down. All right. So let's get a figure there. I'm going to put this in here and I'm going to erase all this because I'm going to need space now. So by using momentum, we found that P2 final at that instant is equal to minus 1.74 meters per second. So now, if the spring constant K is 600 newtons per meter, we're going to find the value of the compression, X. One half, 1.60, 4.00 squared, minus 1/2 of M1. So again, 1/2, 1.60 times 3.00 squared plus, so I can do this, plus 1/2 of the mass, 2.10 times negative, doesn't matter, right? Because it's already squared. Minus energy plus energy, difference of energies together, 1/2 K squared. Well, I mean, there are many factors in common. So, for example, wait, what did I do? It's 2.0, right? Well, let's see what we get. One half, 1.6, 4 squared, 1/2. So that all becomes this. Uh, 16 minus 9 is 7. 2.5 squared minus 1.7. .22. Right? If I do that, that's equal to this. Let's take a look. Half, right? This half cancel with this half, with this half. All right. So 0.022 plus 2.10, 3.22, 6.6 to 600 squared. So X will be that. If I add that, divided by 600, square root, I get 0.17 frequency. It's a very complete problem on elastic collisions that also combines with some of the energy that we did before.